an email, please verify that and log in. If you've already done that and you're trying to get to Databricks to set up the cluster, most likely you'll end up with the landing page of Databricks, which looks like this one over here. Because the cluster to spin up will take about 5 or 7 minutes, we're going to get started on that part first, and then we can continue with the workshop. So basically, it's a simple navigation. We have the home button, we have the workspace, the recents, data, the clusters. So please head over to clusters. For me, I've created this one, but I'll erase it, delete the cluster and start over fresh, just like everyone else. So I'll click on create cluster. You can name it pretty much whatever you feel like. So I'll say Vancouver DataJam. For the Databricks runtime version, please go with the latest one that has ML. We don't worry about the GPU version, just 7.2 ML. So that way we have most of the package. Then once you do that, leave everything else as default and hit create cluster. And then you will see the green circle spinning. That will create the cluster and spin it up. So that will probably take about 5 minutes or so. And then we can go back and set up our packages. All right. So for today's agenda, basically we've done the setup for Databricks. We also have the links for other tools if you guys need them. In terms of the content, I'll briefly talk about data science and machine learning, mainly focusing on supervised learning. Then I'll talk about decision trees. We'll get to practice a little bit of examples on decision trees. We'll probably have a quick 10-minute break. Then we'll go back to random forest. And then probably take another 10 minutes around 7:20. That will leave us with the last hour to go through some examples on your own and allow some time for questions. And all this material, by the way, has been uploaded to my GitHub and should be available on GitHub right away. And the links for the GitHub are in the Slack channel. And also I've included that in the notebooks as well. All right. Thank you everyone for joining us today. And let's dive into this workshop. So we're going to be using R for this workshop. And it's going to be an introductory one into decision trees and random forests. We're assuming that you have some background in R and you have some knowledge of stats and some knowledge of some basic model building and evaluation. So as I mentioned, we're just going to cover the introduction. We're not focusing on the best practices. We're not covering all the aspects of end-to-end machine learning and model building. We're not going to talk about feature selection or proper train test splits or data processing or proper model tuning. Just a quick introduction into the decision trees and random forests. Okay. All right. So what is data science and what's machine learning? So data science and machine learning, most of the time they focus on data analytics, data mining. Usually they involve a little bit of statistics. Sometimes they may involve big data. And also data science is not always about machine learning, but sometimes it could be about machine learning and predictive analytics. Basically, data science is making sense of the data. It's multidisciplinary, involves stats, math, computer science, and of course domain expertise. So I always like to talk about the data science lifecycle from the CRISPR DM methodology. So it's a cross-industry standard for processing data. applies to data mining as well as data science. So basically, once we have a data or once we have a business understanding of the problem, we try to get an understanding about the data. Once we have an understanding of the data, that's where we start diving into the data preparation, the modeling, the evaluation, and the deployment. And it's almost always, it's a life cycle, because at every step, you're going to go back and see, okay, is this kind of the data that I need? Is this answering the business problem that we have? Is this enough data? Does the evaluation work? Does it address the problem? That's why it's a life cycle. Another kind of introductory, I guess, life cycle would be the team data science process, where it's an agile methodology for data science to deliver predictive analytics and intelligent applications. Again, similar problem here, just a bit more details. It will involve capturing the data, data cleanup, exploration, data wrangling, et cetera, as well as for the modeling aspects. It will include the feature engineering, the model training, and the model evaluation. So for today, we're not going to focus. We're just going to talk about decision trees and random forest and the model training aspects. And so yeah, for machine learning, also according to Arthur Samuel, is basically it's allowing the computers to learn from the data. That's when they even improve themselves without being explicitly programmed. So it's as opposed to FLs or explicit programming, machine learning will allow the machines to learn and improve based on that data. In terms of types of machine learning, the main three types would be supervised learning, unsupervised learning, and reinforcement learning. For the supervised learning, we have classification, such as spam, no spam, disease, no disease. So having two classes or more and trying to classify the data into them, or regression. That'll be the value for dollars or weight, trying to predict, for example, the housing market or the weight and continuous data, basically. For unsupervised learning, it's about clustering. So whether there's inherent grouping in the data, association, if there's rules describing the data. For example, if people buy product X, they also tend to buy product B. And reinforcement learning, that's basically when the learning is done by interacting with the environments. So again, for today, we'll be focusing on the supervised learning and diving into the decision trees and the first. So as I mentioned, for classification, it's basically, for example, could be cancer or benign, or obtaining between two classes, two labels or more. For regression, basically how much will the service cost. Similarly, matching, basically recommender systems, and clustering, if there's, we're trying to find natural groups within the data. In terms of application of data science, there's obviously a lot of applications, from fraud and risk detection, healthcare, internet search, targeted advertising, and so on. Of course, just having the machine learning models and the data science applications on its own is not enough. Most of the time, they tend to get deployed in a production system. We're not going to worry about this here, but there's a lot of examples and there's a lot of ways to deploy machine learning models. I'm not going to cover the rest of those slides here, but they're available on the GitHub for more information. I've included a few references as well as additional resources. So there's a Databricks YouTube channel, which covers about the Databricks product, as well as some kind of introductory data science and machine learning. Another way is always to practice, to improve yourself in data science and machine learning. Kaggle is a popular one for competitions and to practice on old data sets. In terms of meetups, at least in Vancouver, we have the Our Ladies Vancouver. We have the Learn Data Science, Women Who Code Vancouver, and Pi Ladies Vancouver. They're not specific on data science and machine learning, but they will have some topics on that as well. And in terms of books and additional resources, there's the big book of R, which has a lot of resources about different R books. And there's also always, like, if you want to get started in machine learning mastery is an amazing website that covers a lot of introductory and advanced topics in R and Python. All right, let's get into decision trees. So here we're not focused on the best way to perform the modeling. Instead, we're focusing on getting the introduction and getting started with the decision trees. So okay, let's do a quick poll in Slack. Who has done some modeling in the past? Let me do that.
What do you include in modeling?
Any statistical modeling.
Okay.
Hopefully that works. Okay, great. So most of you guys have seen this. Basically, doing a simple linear model. A lot of the time, we have done this in school. We've done this in a lot of courses. So if you were to do this, okay, so let's see if our cluster. Okay, so our cluster is up and running. So I'm going to head over here to this setup, attach the cluster to this notebook. I'm going to get those packages installed. That should take a few minutes. Yeah, so basically with the linear models and basic statistical models, most of us have seen that in some way, either through courses or through our experience as well. So here I'm just showing a simple linear model, basically with the diamonds data sets. Let's see if that's still taking some time. So we'll give it, I didn't attach a cluster. Okay, so let's see if that works. Okay, so attaching the diamonds data sets, and we're trying to fit a linear model of the price against all the features. So that builds the model objects. And then we try to predict the model on the diamonds data sets and assign those values to P. So let's do a quick exploration to diamonds. If I display the head of diamonds, we can see we have a few features about the diamond data sets. And then we also have the price. So basically, we fit the linear model of price with all the features included here. And if we click on summary of the model, we can see the basic formula basically for our model, what we have done, and some information about the residuals, the coefficients, and the various features that we have in the model, along with their associated p-values. Now, in terms of p, basically the prediction that we have, if we take a quick look at that one, basically it goes from negative 4,000 to 39,000. And if we were just to display the first few values of p, we get to see kind of what the model has predicted. So obviously, it doesn't make sense to see negative values for price. But here we're just showing the example of linear model more than the application. Okay, so to dive into decision trees. So basically, decision trees are tree-based models. They're non-parametric algorithms. They tend to partition the feature space into smaller regions with similar response values. The predictions are obtained by fitting a simpler model in each region and they work on the divide and conquer methodology. So one popular methodology is the CART, which is constructing decision trees with the classification and the regression tree algorithm. That one works with partitioning the data into homogeneous subgroups and fits simple constants in each node. The models basically are done, they're predicted based on the average responses in the values, if it's a regression problem, and the class that has the majority representation if it's a classification problem. So here's an example decision tree. I'm sure most of us are familiar with the decision trees. For example, if this is the animal decision tree, it works with the head node, for example, has feathers, true or false, can fly, true or false, and then based on that, we can classify the animals. Another way to look at decision trees, basically we have the root node at the top, and then for each branch or subtree, we have decision nodes, and then we have the terminal nodes. So in this case, A is parent of node B and C. Then at each node, we have the splitting, or kind of the decision, basically. So how do we do that in R? Basically, with the library rpart, that's at least one way of doing that. We can install, if you haven't installed that already, but install the library rpart, load the library, and same thing that we have basically fitted the linear model. We fit this using the rpart function. And here we're using the iris datasets. I'm sure most of us are familiar with the iris datasets. And we're trying to predict the species with all the features within the data. So using this function, we can fit the model. And a way to visualize this, we can just plot the model and add the text for the model as well. So if we were to do that, fitting the model and displaying it, we can see that we have the root node, the petal length, determining to see if it's less than a certain value. If it is, then it predicts this class. If it's larger than this value, then there's another decision tree or another node, and then goes to the next variable for the petal width based on a certain value, and does the classification for the rest of the classes. So basically, it builds the tree until we're done with all the features and the classes that we have. So if you're not familiar with the iris dataset, so it's basically 150 rows that we have in the iris dataset, and we display the first few values of iris. Basically, we have the features, 4 features, with some information about them, as well as the species and the classes of the species. So to take another look at that. So here we can see that we have 3 classes or 3 species and how many in each one of them. Another way to visualize the model, instead of plotting the tree, we can also print a model, just like this, and that will show us basically how big the data set is. So we have 150, and that will explain basically the node, the splits, the number of observations, the loss, the Y value, as well as the probability that we have. And then if we have an asterisk here, then it's a terminal node. So this one's such a simple and small tree. So we can see the root node has all 150 observations. And then we have the probabilities, obviously. And then we have the next one, the petal length. Then after that, we see that it splits and goes with the petal width as well, if it's greater than a certain value, and goes on to the next decision and provides basically the probabilities for each class. Okay, so basically the next part would be, how do we partition the tree? So in this case, we're using the CART algorithm that basically has a binary recursing partitioning method. So it's recursive because each split or rule depends on the split above. And the objective is that each node is to find the best feature to partition the remaining data in the regions that we have. Once we find the best feature split combination, the data is partitioned into the regions, and the split process is repeated, basically. And most of the time, a way to end the decision tree or how to stop, it can be done either using early stopping or pruning. Most of the time, we want to avoid having a deep decision tree. So two ways to do that, either with early stopping, you can specify basically a tree depth restriction or a number of observations allowed in any terminal node. Another method would be pruning. Once you grow a very large complex tree, you start pruning until you have an optimal subtree. All right, so let's go ahead and start with this exercise. So here we're using the PIMA Indian diabetes 2 data sets from the package ML bench. So if we were to go into this one. So let me zoom in a little bit, that's too much. So the PIMA Indians diabetes database, basically it's a data set that have around 800 observations and 9 variables from the package ML bench. Basically, the format, one of the features of one of the variables that we have is pregnant. So we have number of times pregnant, glucose, so the plasma glucose concentration. We have the pressure, so that's referring to the diastolic blood pressure. Then we have the triceps skin fold thickness, the 2-hour insulin, serum insulin level. You have the body mass index, the pedigree, whether there's a diabetes pedigree function, the age, and then at the end we have the class variable. So here, to do that, first I load the data sets and I specify the package ML bench. And then once we load the data, we remove any NAs within the data sets. And we just take a quick look at the data sets. As we can see here, we have the features as well as the class of the data set. So let's do a quick decision tree on this data set, and then we'll have some time to give you guys a chance to try that on your own. So the first thing here, I'm setting the seed of 1, 2, 3. So it's a good idea to always set the seed when you're building models. That way it helps with the reproducibility of your models and your data. Once I do that, I'm splitting my data sets into training samples as well as testing samples. I'm using that with the create data partition function and specifying an 80% split. So that will be saved in the training samples. And based on this, we can do the splits of the training 80% and 20% for testing. Usually that's a good practice to split your data sets, train and test, and build the model on the training sets and evaluate how well you do on the testing sets. So let's go ahead and do that one. Once we do that, we want to fit the model decision trees the same as we have demonstrated above on the iris data sets. We want to fit it here for the on the trained data. And the class that we have is the diabetes for all the features. And we are specifying that we want to have a classification here. So we'll fit that to model 1. And then once we do that, we want to plot the model or the decision tree. Okay, so if we do that, we see this decision tree starting with this node for glucose after with a threshold of 127.5. And then we have basically a subtree here with the next feature, which is age, then insulin. And on the other side, we have, again, another tree with glucose. Then we have age, triceps, pressure, until we reach all the way to the end of the features. And then based on each classification or each decision, we classify as being positive or negative. Okay, so Once we did this, we go on to the next part to predict using our model on the test data set that we split above, and we save that in the predicted classes. So if we do that, and we're going to do the head, so we can see, because we specified class, we're getting back the classes for each, or at least the first 6 observations of our test data. So quickly, if you want to compare the accuracy of our predicted classes versus the test data sets, we can just look at the mean. This is just kind of a lazy way of looking at the model accuracy on the test data. And it's showing about 76% accuracy here. So if you want to basically improve upon this, one way we could do is basically prune our tree and see if we can improve upon that. So to do that is basically fitting the model again, using the same data set, same class and the features. However, I'm using train instead of rpart here. I'm specifying rpart within the method, and I'm also specifying a train control function with cross-validation and the number of cross-validations with the tune length. So let's talk about the train function here. So one way to do that would be !train, so we can see the help information about the train function. So it comes back from the caret package, and that helps us train our model. So the nice thing about the caret package, we can train any kind of model. So we can see in the help and the documentation here, they're using RF, which stands for random forest. But we can use and specify any model, or almost any model within the caret function. So in our case, we're choosing rpart to do that. Okay, and this is for the train function. And then let's say we want to know more about the train control. So the train control, again, it's also from the caret function. It's control parameters for our training function. That helps us basically with the complete computation of the training function and pruning or training the model. So the methods here basically specifies what kind of method we're trying to go with. Basically the resampling method. The default is boot, but we have specified CV, which stands for cross-validation. We could go with the repeated cross-validation. We could go with leave one out cross-validation, etc., etc. There's more help provided in the references, or if you dig deeper into the help of the caret library. So once we specify that, let's assign this to model 2 and plot model 2 as well. So here, the difference, because we're using the train function, when we plot model 2, we get back the accuracy of the cross-validation on the training runs that we have with the complexity parameter. So we can see here the highest accuracy is around 76, and we have the lowest one around 74 or 75. So just above 76, and starts around CP, I guess 0.27. And yeah, so if you want to look at so instead of guessing and estimating what's the best way, we can just go with model 2 and get basically the best tune, and that will provide the best parameter for that one. So we wanna also plot the model or the final model that we have here. So model 2, since we've done the tuning, we do get the final model back. So if we end up plotting this, we end up with this decision tree. But this is decision tree. It's only with one feature. It's probably not very helpful here. But it basically estimated that only one feature is enough to do the classification. Now, is this doing better than our initial model? We can find that out. So we can do prediction on the test data sets that we specified above, and we can look at the mean or the accuracy of the mean per weight classes versus the test data. So running that gives us back a 73% accuracy, which is slightly lower than our original model. So in this case, it was not a good one, and we need to go back and train the model more. So before we end here, let's jump to the third notebook and try out. Okay, so let's jump to this notebook where we have a data set. So if you're trying to practice and go along with us, if you haven't installed the packages, please make sure to install the packages on Databricks cluster. If you're doing that locally, please make sure to install any additional packages that we have highlighted in the Slack channel that you don't have, for example, Tidyverse, Carrot, Arpart, etc. Get that installed as well. So if you have done that already, so we can load those packages. So we need Carrot, the E1071, Arpart, and Tidyverse. Oops. And then the data set that we're going to be working with right now is from the NAS package. And here's the link for this data set from the Toronto Computer Science Department. It's the Boston housing data sets. It's derived from the US Census data in the Boston area. So the data set name in R is Boston. We have about 14 variables here. They're not very well labeled, but the first one, CRIM, basically talks about the crime rates in that town. ZN would talk about the proportion of residential land zoned for a specific lot area. INDS is the proportion of non-retail businesses per town. CHAS is the Charles River dummy variable, basically tracks Bound River or otherwise. NOx is the nitric oxide concentration. RM is the average number of rooms. Then we have the age, the owner occupied. We have the weighted distance to the 5 Boston employment centers, and the accessibility of the radial highways, property tax per 10,000, and then we have the pupil-teacher ratio by 10. The BK is the blocks by 10, and then LSTAT is basically the percent lower size of the population, and then the median value of the owner-occupied homes in 1,000s. So let's go back to our notebook here. So if we load the data and we look at the first few lines, so we have the variables we talked about, and then we have our median value of the property in the thousands, and that's basically the variable we want to train or predict. So let's load the data sets and build the decision tree to predict the median value. So what we have shown so far was classification, but here we're trying to use regression. So I'm gonna probably provide everyone, let's give everybody about 5-10 minutes or so to get you guys started with this. And then once you're done, I'll just let us know on the Slack channel and we can pick it up from there. I'll put the poll in the Slack channel for now, and then I'll I guess no one voted on the more time, and also no one else other than Kristen voted on the done part. So let's do this together then. So kind of what's the first step that we need to do here? First, we'll obviously we loaded up the data. Would be to set the seeds, and then I guess create our training sets, partition the data into training and testing. So let's do that. We do this. Again, you see I've set the seeds. So I'm using the same seeds here again, doing an 80-20 split. And we have our training and testing data here as well. So the next part, let's fit the model. We're going to use the train function from caret, using the median, the median value, R parts, and then with the cross validation. And let's see what we get. Okay, so because we're using regression here, the metric is RMSE for the cross validation, and we can see it keeps going up. It starts here around 5 and goes up to 8. So with accuracy, the higher the better. With RMSE, it's the other way around. So if you look at the best tune here, we see it's at 0.015. So it's perhaps this point right here that will give us the lowest RMSE. So let's see how this final model looks like if you want to visualize it. So again, we plot the final model that we just created and see how that works. So it works with the first feature that we have is RM. So let's see what's. What do we have? So yeah, this feature here being at the top, then on the left-hand side, so the subtree, we have the percent stat, and then the criminology, and then we have the LSAT as well. On the right-hand side, we have this subtree as well, where we have, again, we split on the RM, and then the LSAT as well. And based off that, see here we get values instead of classes, because we're doing regression. And I guess let's do a quick look into the model. So if you want to take a look at the model instead of plotting it into text, we can see basically the observations that we have and the nodes as well as the splits, the variance and the Y valuation of the value that we have. And then, so okay, let's do some predicting the test data and see how that looks like. Okay, so we predict our test data, save that to predictions, and we look at the first few observations. So let's see what was the original median values in the data set for the testing data sets. So if we look at the summary, it goes from 5 to 50. However, in our predictions, it goes between 11.8 to 44.73. So it's not quite as spread as our I guess values in the test data. So here to see how well we did, let's look at the RMSE instead of the accuracy. So if we run that, the predictions against our test data, we get 4.48. So a bit higher than in our training data. So I think that was probably around maybe 2.5 or something like this. So it's a bit higher than what we got in the training data. So we expect that it's as in terms of the prediction. So one way we can do this is, in a crude way, just plot the predictions versus the median values and fit an A/B line through the points. So if you take a look here, so y-axis we have the actual values, on our x-axis we have the predictions. So we can see it's not doing too well. That's why the RMSE value is a bit high here. So that's that's what we have for decision trees. If we go back here in terms of takeaways, so decision trees are simple and easy to implement. It doesn't require a lot of pre-processing. It handles different variables, category variables, and missing values. It's not great on predictive accuracy, and deep trees tend to have high variance, and on the other hand, shallow trees tend to have high bias. So a problem with decision trees, such as the CART algorithm, if we're talking more about the technical aspects, it's a greedy algorithm. Even if you use bagging, decision trees can have a lot of structural similarities and have high correlation in their predictions. So another way to think about data in decision trees, so the great advantage of decision trees, it makes complex decision making simpler and breaks it down into smaller, simpler decisions using the divide and conquer strategy. And it identifies a set of if-else conditions to split the data according to the values of the features that we have. So that's what we have for decision trees. So let's take a 10-minute break and come back to dive into random forest. So right now it's 6:23. So let's come back at 6:35. All right. Hopefully everyone is back from the quick break. Just a reminder, folks, we're recording this event to make it available in the future for everyone, since we're running the workshops concurrently. However, if you feel comfortable and knowing that we're recording, please turn your cameras on to make it easy for me to see you guys as well for the workshop. We also did notice there was a small issue with a simple poll, and then we're going to switch that to a different way to vote in the workshops. All right. So before we jump into random forest, let's read what everyone has posted about themselves on the Slack channel. Let's see what everyone's been up to. So hopefully I'm not butchering any names, and apologies in advance. But Almas is saying you've been cooking a vegan pad thai. That sounds pretty cool. Emma has been relearning the clarinet. That's nice. Lucia, she was saying she's learning how to create botanical dyes. Nice. And Nabila, you've been your baking skills. Oh, tiramisu. Okay, nice. We'll definitely ask for the recipe after the workshop. Hopefully, you can meditation. Nice. Definitely needed during this pandemic. Amanda, you've been going back to the piano and baked chocolate chip cookies. That's cool. Shannon, she's been learning to write with her left hand. Hopefully that's going well. And
I, of course, tried that immediately once you sent that message.
cool. Kristen, you've been, your music theater is waitress. Okay, cool. I haven't seen that one. And
Yeah, it's
Roshni,
excellent. They came to the Queen Elizabeth Theater last season to perform, and it was really good.
oh, I guess you're lucky that you caught it before.
Before the COVID closures of all the live productions. Very fortunate.
Cool, nice. And Roshni, been forcing to cook more and more, or using Instant Pot. Palak dal. Oh, so you've been making palak dal, which is lentils with spinach. That sounds interesting and healthy. Hopefully, I'll get to try that one day. All right, cool. Again, guys, if you need any help, please post in the channel or reach out to one of the helpers. We have Lucia, we have Kristen, we have Shannon. And yeah, if you guys need more time or if I'm going too fast, please let me know. All right, so let's get back into our workshop. So our next topic after decision trees kind of makes sense to go into random forests. So why are we talking about random forest today? So random forest is first, it's a popular machine learning algorithm. It's a type of ensemble model. So what does that mean? It's basically, you can think of it as bootstrap aggregation or bagging. And random forest algorithm makes a small tweak to bagging and basically results in a very powerful classifier. So random forest is a small modification, as I mentioned, to bag decision trees and builds a large collection of correlated trees for the basic idea of improving predictive performance. They're very popular algorithms out of the box or off the shelf, and they have a good predictive performance with a little bit of, or at least little hyperparameter tuning. There's a lot of modern implementations in random forests, but the most popular one, the Freeman's algorithm, has become more of the, I guess, the dominant one. So let's see what random forest is all about. So basically, hopefully this picture is not too unclear for you guys, but random forest is basically a bunch of decision trees. As we can see here, we have tree 1 all the way to tree n, and working with if it's a classification problem, works with the majority voting to determine the final class of each of those decision trees. And if it's a regression, works with combining the scores. So random forest, sometimes is referred to as RF, improves the performance of a single decision tree by taking the average of many trees. So that's what an ensemble method or the model averaging approach. So why do we call it random? Each tree is a bagged sample and a subset of all the predictors used as a candidate at each split. Reduce the number for predictor candidates at each split, allowing for something other than the best split to be the top split here. Thus growing many different trees, and they're correlated trees. So that's the random, where the random comes from. Why do we call it forests? Just because we have a lot of trees. We grow a lot of trees within the random forest algorithm, and that's where the name came from. So we probably mentioned a few kind of terminologies that maybe not everyone's familiar with. The first one we'll talk about is bootstrapping. So what's bootstrapping? Basically a powerful statistical method for estimating quantity from a data sample. Know that our samples know that our mean has error in it. So how do we bootstrap? So for example, we create 1,000 random subsamples of our data set with replacements. We calculate the mean of each subsample, and then we calculate the average of all those collected means to give us the estimated mean of the data. So basically, that's the basic idea of bootstrap. Now, the step after that would be the bootstrap aggregation or bagging. Takes it a bit further. So basically, it's a simple, powerful ensemble method. It's a technique that combines the predictions from multiple machine learning algorithms to have something more accurate in predicting than an individual model. So it doesn't have to be decision trees, doesn't have to be the same algorithm. It could be a bunch of multiple machine learning models. So bagging is the application of the bootstrap procedure to a high variance machine learning algorithm. So how does it work? So basically we create 100 random subsamples of our data. We train, for example, in decision trees, or in this example, we train the correct model on each of those subsamples. And then given the new data sets, we calculate the average prediction from each model. And that's how we get the bagging or the bootstrap aggregation. So as we mentioned, random forest is basically an improvement over the bagged decision trees. So we're trying to have something better than the subtrees. And it's a simple tweak in this case over the CART algorithm. So let's talk a little bit about some of the tuning parameters or some of the parameters for random forest. The most important one I would say would be the split points, sometimes called n or n try in the functions, and that's basically that defines the number of features at each split, and that's one of the most important parameters that we should tune for our cross validation or in the model building. So a good rule of thumb, if we're doing classification, the good default would be the square root of p. In this case, p is our feature space. For regression, then that would be basically the number of features divided by 3. So let's, for example, let's say we have a data set that has 25 input variables, and we're doing a classification problem. So if we have 25, and taking the square root of 25 would be 5 in this case. So another point for random forest, how do we estimate the performance if we're doing all those bootstraps? In this case, we're doing, for each bootstrap sample, we're doing something that's looking at the samples that have been left behind and not included in our training data. That's something called out-of-bag samples, or OOB for short. And then the performance of each model is basically taken on those left-out samples and averaged to give us the estimated accuracy of the bag models. And that way gives us a reliable test error estimates and correlates with our cross-validation estimates. Another point we can use random forest for would be the variable importance. So every time we do the bag decision trees, we construct them. We calculate the errors at each variable at each split points. If it's a regression, we sum those squares. And if it's classification, we get the Gini score. And that way we can also get the variable for our training sets. So yeah, if we're thinking about kind of regression or classification in a random forest context, it can be generalized simply in this way. So first, we have a training set. We select the number of trees to build. That's the n trees in this case. So from I to n trees, we generate a bootstrap sample of the original data, have the regression classification tree to the bootstrap data. And for each split, we get the n try, so then XML or the n try variables at those the splits. And then we pick the best variable split points among the n try. And we split the nodes into the child nodes until we're done, and then we end, and then that way we have our model. And once we end trees, we have the output of the ensemble trees. But a key point here that we're not pruning the trees that come out of the individual trees in the random forest. So instead of talking and having all this text, let's write our example. So first, let's load the necessary libraries. So we need the random forest, the carrots, E1071, and the tidyverse. So I attached the cluster to this notebook. Then I can go ahead and run this cell. Okay, great. If you haven't installed random forest, well, it's included in Databricks ML Databricks runtime. However, in your local setup, if you haven't done that, just make sure you install random forest. So the next step, we'll set the seeds. So I'm choosing a different seed here. And we're looking at the RS data sets that we looked at. So that's another way of splitting the data sets. So we're just doing it I guess the simple way. We get the indices from 1 to n row of the data sets. And based on that, we can split for the training and the validation data sets. So we go ahead and run that one. So the first one way to fit the model, we can call the random forest function from the random forest package. So let's take a quick look at the random forest. So it comes from the random forest package. So we can do both classification and regression. So that's awesome, great. So okay, it implements the Beeman's random forest algorithm. So that's also good. So what's the basic function? So here we see we have the formula. We have also the data. We also have other parameters as well. And then the second one here as well, we see the defaults for each one here. So the default number of trees that we have is 500. For mtry, you see it kind of provides some default as well, where it gets the floor of the square roots, or we get the maximum of the number of columns divided by 3, as we talked about it previously. And then, of course, we have other parameters that we're not going to talk about just yet. And then if we need to dig deeper into each of the arguments, we can go into that. So let's see here. So the number of trees to grow, and try number of variables randomly sampled as candidate at each split. Then explains for classification, kind of what's the default or what's the best way to select the M try, as well as for regression. Okay, great. So let's do that here. So we have the random first. We have the training set from the RS data sets. So we have the class or the species that we're trying to predict with all the features that we have. So we're selecting 100 trees here, and try 2, and we're setting the importance to be true in this case. So let's go ahead and train this model. So let's take a look at this model here. So again, it displays kind of the formula that we have chosen. It also explains how many trees we've selected, the number of variables tried at each split. So here, as I mentioned above, the out-of-bag estimate of the error rate is about 6.67%, and also provides the confusion matrix on our training data sets. So if you guys are not familiar with the confusion matrix, it's basically for classification. It provides the predicted versus the actual classes and tries to do this tabulation. So that's great. So since we have set importance to be true, we can look at the variable importance plot. So the var and plot of the RF classifier will provide us with the variable importance, both using the decrease in accuracy in the plot as well as the decrease in the Gini, because we're doing classification with the Gini index, and kind of ranks the variables with their importance coming out of this model. So I'm not going to go into too much detail about this one, but let's see what we can do with this. So let's predict our classifier on the validation data set that we have and see how well we do with this. So if we do this, actually before that, let's take a look at the predicted classes. So here's the head of the predicted classes. So we can see for the first observations, what is the class, and we have the levels of the 3 classes. So it's not a binary classification here. It's we have 3 classes that we're looking at. And also a quick way to look at the confusion matrix, we can just tabulate our observed results or versus the predicted results here, or the actual versus the predictions. So here we can see that we correctly classified all of them except for 3 over here. So another way that we can look at the performance of the models is the confusion matrix function. So if we look at the help of the confusion matrix, it comes from the caret package. It basically creates a confusion matrix plus, so the tabulation, plus gives us some metrics as well. So it's very simple. We just provide the data and we provide the positive class if needed, and then we get that as well. So here, if we type the confusion matrix with the prediction and the validation, we should get the confusion matrix, so same as above, the tabulation. We have the reference of the actual class and the prediction out of our model. Plus, we have the overall statistics. So we have the accuracy. So our accuracy here is 96%. We also get the confidence intervals for our accuracy. We have the no information rate. So this one is also important. If it's close or similar to your accuracy, then that means your model is not very informative. And you get a p-value of how well is the accuracy is higher or greater than your no information rates. Because my no information rate is 0.35 and my accuracy is 0.96, I have a very small p-value here. You also get Cohen's kappa. For some reason, the Macamoose test p-value is not available here. But we also have the stats by classes. Because it's 3 classes here, we get the sensitivity, specificity, PPV, NPV, prevalence, detection rates, balanced accuracy for the 3 classes. So most of the time, when it's a classification problem, we try to emphasize on accuracy, or I want to get the best accuracy, the highest accuracy. So that's not always true. Yes, most of the time that is the case. You train your model to select the highest accuracy. But sometimes, for example, if it's healthcare or CNN models, you want to try to optimize for the positive predicted value or the negative predicted value, or sometimes AUC, or the area under the curve, under the ROC curve. So it just depends on which model we're looking at. Okay, so let's try another example here. We looked at the Pima Indian database data sets earlier with the decision trees. So let's try that on our own using random forest. So here, I'm just gonna show how to load the data. So we're loading the data, specify the package ML bench. Make sure you have this package installed. Then we omit the NAs from our data sets. And then just make sure, look at the data, make sure that it makes sense. And let's get everybody try to get the random forest model on this. And we'll give everyone about 10 minutes or so. And once you're done, please forward in the Slack channel. Let's get into this. So we've loaded the data. We've removed the NAs from our data sets. So let's look into this. First, let's set the seed and split our data sets. So we create the partition with the 80%, and we have our training data and testing data. So let's go ahead and, okay, so looks like I did not load my data in this notebook. Let's try this one more time. Okay, so this worked. So let's give a quick check. Okay, so I have my training data here. Yeah, in case you have questions or needs, and I always say that help is probably the most used command, and this is your best friend, probably more important than Googling. But you can always do question mark, create data partition. We'll explain the how to use the function, the documentation here. So we've set the seed. We use the random forest function. So diabetes is the class we're going for, using all the features. Train.data is our training data here. Let's use 100 trees with mtry of 2 and get the importance. So let's see how this one's going to work. Okay, perfect. Let's make some predictions on our testing data sets, and we're going to specify class to get the classes back. Okay, so we can see that we have the negative versus positive classes. Always make sure that your predicted classes are the same as your actual classes. So one way to look at that class. This one. So here I have a factor. And our class for these is also a factor. So that's a quick check if you run into a problem. Another one would be to look at the actual results, so tabulate both results. For the predicted classes, I have the NEG or negative, POC positive, and same thing here. So the classes match. So that's good. So let's go ahead and check how we did for the predicted classes on the testing data sets. So let's run the confusion matrix. So we get the confusion matrix coming out of this. Since it's a binary classification, we just get a 2x2 matrix. So we can see here we predicted correctly 43 negative and 19 positive. However, we have 7 and 9 misclassified on other way the confusion matrix. So it's always the confusion matrix is a good idea to give you how you're doing. So because we have misclassified a few samples, our accuracy is just under 80%. Because we have a small sample size, we have somewhat of a large confidence interval. So how are we doing compared to the no information rates? It's okay. Still significant, but it's not too great. We have a coherence kappa here as well. We have a nice p-value test, and then because it's binary, we only get one value here for the for those metrics: the sensitivity, specificity, PPV, NPV, and the detection values. And notice at the end, we have the positive class, and it says here it's negative. So no, that's not what I wanted. The positive class should be positive. So what should we do here? Again, going back to the help functions here, we see, oops, the confusion matrix, my bad. So let's do that. Okay, so looking at the positive class. So let's see what's the argument for that one. Okay, so we should specify the positive class in this case. We can set the positive class to pause, then run this one more time. So you'll notice the sensitivity and the specificity has flipped, and at the bottom, our positive class has been set to positive. Okay, so this makes more sense. And notice, just because we have probably uneven classes, we have our balanced accuracy slightly different than the accuracy. So that's something to pay attention to, especially if you have imbalanced data sets. Okay, great. So let's kind of look at our takeaways here from the random forest. So we can see with a little bit of, I guess, with no effort at all, we were able to get a good predictive accuracy, basically out of the box algorithm that we use here. So that's great. It's and if we compare our accuracy here with the decision trees, I think that was in the first one or the second one maybe. Oops. How did that? Is it not here? Okay, bear with me. So let me look. I think for the first one, what was our accuracy here? Okay, so it was 75 accuracy. And when we pruned the tree, it even went down, but let's not look at that. It's about 75 with random forest without any tuning. We got slightly higher accuracy. So we have all the benefits of decision tree, of course, with the exception of the sorted splits. We also have the benefit of the bagging reducing the instability between the tree correlation. And then we have the added split variable selection attributes. With random forest, we have a faster tagging with the smaller features at each split. Now, saying all these advantages, what is the drawbacks of random forest? Why don't we use it all the time? So random forest, it's a bit slow. It's computationally intensive, especially when your data gets larger. Similar to bagging, the algorithm has independent steps. However, the modern implementations, for example, the ranger function H2O, even with caret, even with the random forest, you can use it with parallelization and parallelize your process across the different threads in your CPU or the different nodes if you have a cluster. That way you can speed up the process. We're not going to cover parallelization here, but if this is something you're trying to look into, you can Google or look at the references I provided for further help with the parallelization of your random forest model building. All right, so this is the end of the second part of our random forests. So we're probably a little bit ahead of schedule. So let's take a 15-minute break and come back at 7:30. That way we have for the last part to try out building decision trees and random forests on the same data sets. And we can compare both models to see how we have done. We'll get you guys to get to do this one on your own. And then we can look at the solution as well. And if you guys have any questions as well, we can answer them in that part. So it's 7:13 right now. Let's come back at 7:30. If anyone is back from the break, there was a question about the seeds and why using the same seeds did not generate the same results as I've shown in the notebook. So Kristen has pointed out that an older version of R may have caused this, and there was a change the way that the sample basically works in version 3.6. And while we wait for everyone to be back, if you're not familiar with Databricks, again, as I mentioned, you have the landing page with some common tasks, such as creating a new notebook, a table for your data, a cluster. We're only allowed one cluster. You can schedule jobs. I think this is probably not available for the community edition. You can create an ML flow experiment. You can import a library and have the documentation of it, obviously. The recent notebooks that you have and additional information. So here from the pane, this will take you to the home, which is the same as the workspace. If you have other users shared with other users, they will be shown here. If you have different folders, they will be available for you. You can create new folders. You can also import the notebooks or source files. If you have the data or the source code already on your local computer and accepts quite a different formats, you can browse or drop the file here. Or if you have a URL from, let's say, GitHub with those formats, you can just import it here. So for example, for the workshop source code that's available on the GitHub repo, you can just use the URL to import the notebooks one by one, or the source code of the R code. Data that's, if you're uploading data or spinning a Spark cluster, so Databricks is big on Spark, you will find that here. Clusters, as I mentioned, we only have one. You have quite a bit of Databricks runtime versions. If you're running machine learning, just make sure that your runtime has ML. jobs, well, this is not for our community edition, but if you had the enterprise Databricks, you can schedule notebooks to run here with a specified cron schedule. Something cool about the notebooks within Databricks. First, you can click here to see about the shortcuts. You can collaborate. So if you have other members in the same projects, in the same team working together, they can comment, just like with Word or Google Docs, on the code and see these things. As I mentioned, if you have the ML flow experiments, if you've been running that, you get to see that one here. And this one, so the kind of the sad part is the community edition does not allow us to link it to Git or any repository. GitHub here, even this option is available. The changes and the version history is available built in with Databricks. It's only available within this notebook. It's not publicly shared and it's specified with the shared body. Here you have some, I guess, drop-down menu. If you want to clone the notebook, rename it. If you want to change the default language, so you can notice here I have R as the default language. If I want to change the default language, I can specify here. I can get to pick between Python, Scala, SQL, and R. Even if you're working with R in the default as the default language, you can always specify with the % command or the magic command another language such as Markdown. If you're using R or Python for Python and Scala. And you can also specify if you want to share the standard default results only side by side. That can be handy for presentations. All right, hopefully everyone is back from the break. So let's head back to the last part. So here we're looking at Notebook 5a, so the try building model. All right, so for this part, we're going to try to build the model on the same data sets using both decision trees and random forest and compare both models. So the data set here is the car evaluation data sets. So you can see this from the UCI. So I have that here for the link. So let me just click on the link, take me to this data set. The car.data is the file, car.names is the header. If we remove all this, and let's just go back to the UCI ML repo. So here you can see, hopefully it's not too small for everyone, but you can see kind of the newest data sets that they have and the most popular data sets since 2007. Iris, obviously one of the top ones that we have looked at. The car evaluation, we're going to look at this one here. I think we looked at some other data set as well here. But yeah, those are the ones from the UCI. We looked at obviously other data sets that were part of the ML bench and the mass package. So let's take a look at the car evaluation. So this data set, it's a bit old, from '97. And we have some information about the data. It says that we don't have any missing values. We have 6 attributes for the data, around 1,700. We also have some information about the data. We have the dataset information as well as the attribute information. So for the class values, we have MX, so unacceptable, acceptable, good, and very good. And then for the attributes, we have buying, very high, high, medium, and low. Maintenance, same thing. And then the number of doors, 2, 3, 4, 5, more. How many people or persons in the car, that you can fit in, 2, 4, more. The log boots, small, medium, big. Safety, low, medium, and high. So let's go back to our notebook. So what we're trying to do here, predict the condition of cars based on the features provided. So as I mentioned, let's try this both with building a decision tree and random forest models and compare their performance to each other. So first, what's the first step we gotta do? So let's give you a little bit of tips. So first, load the packages. Since this is a new notebook, if you're using Databricks, we should load the packages. So random forest rpart carrots. The second step, we gotta load the data and then split the data. So in order to load the data, I've provided this for you, but I'm gonna paste this in the Slack channel. Hopefully that works. You can use that to load the data from the URL, so you don't have to load the data and worry about that part. And then if we end up, okay, so let's load the data. And then if we display the head of the data, we notice that we're missing the names, the column names. Okay, so let's since the names, so there were basically different parts. So this is different, okay, that's good. So let's use this for everyone. That way we're not we're all using the same column names for our data. So let's go ahead and set the column names and look at the first few observations. So we see the buying price, very high, maintenance very high, number of doors, number of persons, wood space, safety, then condition. So let's do a quick tabulation of the condition. So we have acceptable, good, unacceptable, and very good. So if we look at the structure of the data, we already know that we have around 1,700 observations. So the 7 variables, the 6 plus the class. If you look at the summary of our data, we get basic information about our data. So next, let you guys try that on your own. Let's give it a bit of time to try building both a random forest and decision tree models, compare the performance. If you get stuck, if you have questions, please post them, and we'll go from there. I'm not going to set a specific time here, but I'll probably post a quick voting poll to see how people are doing, if they need more help. If you do run into errors or problems, we're here to help. A good way to troubleshoot would be to first look at the first few observations of your training sets to match your original data using the head command. Also doing summary on both the original data and the training data to understand kind of what is the data that you have in case there are any issues. And also in R, it is case specific, so make sure that you have the correct uppercase, lowercase for the features in the class. Okay, so let's carry on, and we'll wait for the screenshot, and we can help you in a bit. So, okay, so first I'm starting here with building a random forest model. So I'm fitting that model for the class, that the condition with all the features for the train sets that I've just created up here with the 70-30 splits. So let's take a look at this model here. So looks like I don't have my packages loaded in this notebook? Okay, perfect. We have, okay, so let's try this one more time. Okay, great. And looking at model one, so we're using, even though I have not specified the number of trees, but we're using the number of trees to be 500 here. And if left the n tries the default, so we'll end up being 2, and provided the out-of-bag estimate error here, 3.81. And then we have a quick confusion matrix on my training sets. So you can see even with the training set, it's not perfect, but it captures quite a bit of them. So let's give it a quick tune here for model 2. I'm going to use 500 trees, and I'm going to try and try to be 6. So let's take a quick look at that. So here we can see that we have a smaller error rate on our training sets. Let's predict and see how well we do here. Okay, so on the training sets, so we can see looks pretty good. So let's see how this does on the validation sets. So if I'm doing it just crudely with the mean, I get 98%. So let's see the confusion matrix. I'm doing this on the fly, hopefully I don't make any typos. Okay, perfect. So there is some misclassification. We can see that in the confusion matrix. The majority are not too much, except for this one here. Sorry, for 1, 2, and 3. Okay, so it's not a lot. So my accuracy is 98%, kind of similar to what we have seen here. It is higher than my unit information rate, so that's good. I have a significant p-value. My coordinates kappa is available. And then I get to see the different classes. So we have 4 classes here. We get the different sensitivity, specificity, and other statistics by class. So that's good. So let's take a look at. Okay, so Kristen got 97 accuracy. So that's great. So we took a look at this. Yeah, if we want to take a look at the importance, because we specified the importance from model 2, that will give us basically the different metrics for the importance with each class for those features, depending on what you want to look at, the mean decrease in accuracy or the mean decrease in Gini, whatever you're looking at for your features. We're not covering the feature selection and the variable importance here, but feel free to explore on your own. If you were to do a var and importance plot on model 2, you get something similar to this, both with the mean decrease in accuracy and the mean decrease the Gini index. So I'm going to skip this portion here, and let's fit the decision tree and compare the two. So I'm going to load the RPort, the CAR, the E1071 packages. So let's so this one's going to be simple. Train again the training sets and the method RPart specify the code algorithm for the decision trees, and we're going to do the prediction. So okay, so that runs. Okay, so let's take a look at the table for the training sets. So you can see it's not doing that good on the training sets. So on the training set, we get the accuracy about 80%. So let's see how it looks like on the validation sets. Okay, so we get that. I mean, it's not horrible, but we do get some large numbers in the classification here, here, and here. Here. We don't get anything correctly classified for the very good. So if we look at the accuracy here, it's 77.6%. It's kind of expected. Our training was just below 80%. If we were to do a confusion metrics here, yeah, 77%. So it's just slightly higher than the information weight. So the p-value is just around the significance here, and we get the same metrics here. Let's take a look at plotting the. We just need to perhaps do this. Okay. But I need the best model. So if I wanted to take a look at the final model, I can do so, or but I need to get text as well. Otherwise, it just doesn't make sense. I'm just going to copy paste. And I can quickly comment here, model. Okay, so we can see the decision tree for our model here. Okay, we have it here as well. That's fine. Okay, so what was Kristen's accuracy for the decision tree? 86. That's a lot better than what I got. That's great. So we have another individual with 96 in the random forest. Okay, so at least you figured out what was the issue. That's great. Okay. So for the random forest, let's see what we use for our entry and entry. I think we have that just up here. Model 2. So for model 2, I used 500 trees and entry of 6. Okay. Yeah. So we didn't talk a lot about kind of the best way, or at least some of the ways to tune the models, even though random forest doesn't require a lot of tuning or a lot of just works, out of the package. There's a few ways to do so. One way would be a grid search. Another way would be random search. You can either loop or do it in different ways, or some kind of hyperparameter tuning to specify different entries or different entries and see kind of what is the best performance out of those ones. Yes, we mentioned that kind of the default value for entry should be square root of the features, or divided by 3 for the regression. But sometimes it's a good idea to train your model, see how it works to get the best accuracy. So you take a look at your cross-validation accuracy first, then you take a look at the testing sets. Same thing for decision trees. If you're pulling your tree, you can do that as well to get best plots. But usually random forest out of the box for complex data, it just works right away. All right, so that's what we have so far in terms of kind of materials and exercises for today. Before we finish, if you're looking for the code, it's available on my repository that has been posted in the Google Docs, as well as the pinned posts at the top. So I'm just going to go to that one right now. So Haddad C, get username, the Vancouver DataJam Advanced Art Workshop. So the README file contains information as well as kind of how to access R if you're looking for a different version than your local setup. I've also included quite a bit of references that I went through, also the data sets that we looked at. And for the codes, so for the notebooks have been posted under this folder, workshop notebooks. all the different RMD or R Markdown notebooks. So this is usually helpful because it has the magic commands to be imported in Databricks. However, if we're trying this locally, I also provided the code as plain R code for the different notebooks as well. So you can just ignore the Databricks or the generated magic commands, and you have the plain text, and you can import that in your RStudio or local setup. I have only 5A here, but I will post that after the workshop with the solution as well, either today or end of day tomorrow. So we have covered this. I want to go back to the introduction. At the end here, I mentioned about the additional resources. It's probably a good idea to highlight if you're looking for additional information, meetups or YouTube channels. So YouTube, look for the Databricks. There's obviously others, but this is one good group with a lot of, especially for Database Academy and the meetup groups. They record all their meetups. Again, if you want to practice with other data sets, Kaggle provides quite a bit of data sets. Some of them you can even play around and download without signing up. Others are restricted for signing up. Again, with meetups, Our Ladies Vancouver, Learn Data Science, Women Who Code, Our Ladies Vancouver. If you want, I guess, a list of books, Big Book of R, I came across this one. Basically, lists a lot of the books. So by topic for data science, lists a lot of, I guess, the books in R. A lot of these books are done in HTML with the book down package. So you can explore them online or order a print from Amazon or some other local shop. So that's it for today. If you guys have any questions, please post them in the Slack message. Otherwise, please don't forget to fill in the end of workshop survey and enjoy the rest of your evening. Thank you again for your time today. And a special thanks to the helpers, Rashia, Kristen, and Shannon, for your time today. So yeah, now please post your questions and we'll go from there.